Recording in progress.
Good afternoon. My name is Dr. Richardson, and this is lecture 9 of a course entitled An Introduction to Linear Algebra Using Python. Again, my email address is listed below, and you're invited to reach out to me if you have questions on the course, content, problem sets, lectures, or any typos you may encounter. Again, as a reminder, learning is not a passive activity. In addition to watching me in the video clips or in real time, it's important to go over your notes and write them down when viewing the lectures. You have to involve your mind actively, not passively. Problem sets are critical for the course. You'll get nothing out of these lectures unless you do the corresponding problem sets. The solution key to problem set 8 will be posted on the appropriate website this evening, and problem set 9 will be available sometime tomorrow. Again, the problem sets have analytical sections and lab exercises showing you how certain commands in Python are very helpful in understanding and working with the ideas that we've discussed in linear algebra. You can send me an email address at srichards. Send me an email at the address srichards22@comcast.net if you have any questions on the lectures, problem sets, problem set solutions, typos you may have encountered. Perhaps you have different ways to do the problems than I've suggested, so reach out to me. And again, a ruler is doing the problem sets as well as taking the notes of the lecture. This afternoon's lecture, we're going to talk about the inner product of vectors. We've already discussed the inner product of vectors if they're real, if you have a set of real scalars and real vectors. Next, we need to look at the problem of what does it mean to take the inner product of vectors if you're dealing with complex vectors or you're in the complex plane where you have complex scalars. Then for the remaining 9, 10, 11, 12, 13, 5 lectures of the course, we're going to start looking at matrices from a completely new point of view. Up to now, we've looked at matrices as useful devices that store numbers or information. Our new way of looking at matrices will be to recognize that they can be viewed as operators. They will do things. Matrices can act on vectors. And depending on the matrix, they can do lots of interesting things. Okay. So again, we're looking this afternoon at the idea of an inner product. Let's get rid of that, bring that down a bit. So we're looking at inner products this afternoon in today's lecture. But now we're going to extend this idea to complex numbers. So as we discussed last time when we reviewed complex numbers, all the action occurs in the complex plane. The beautiful thing about the complex plane, it allows you to express a complex number as z. And here's a picture of the complex plane, at least in 2 dimensions. The x-axis corresponds to the real part of the complex number, x, and the y-axis corresponds to the imaginary part of the complex number, z. So in fact, you can write your complex number as a point or a vector in this two-dimensional complex plane. Z is given by x plus I, y. Or you can write it as an ordered pair, where x and y are real scalars. So if we're going to make any sense of asking what does it mean to take the inner product of complex vectors, let's review our answer to a previous question. What do we mean by the norm of a complex number? Well, the norm of a complex number is equivalent to the magnitude or length of this vector. And this thing must be real. So if you just took the ideas of vector analysis for real vectors and real scalars and use the definition of a complex number to calculate the norm, magnitude, or length of it, you would use the standard procedure and you'd come up with a quandary. The quandary is that your result is not necessarily real because you have this imaginary part that you have to take the square root of. So this thing is not real. So that's a major headache. So to avoid that headache, the prescription we'll use is we'll take the product of the complex conjugate of the complex number with the original complex number, and then take the square root of that. And let's see how that works out. All you have to do to take the complex conjugate of this complex number, x plus I, y, is replace I by minus I. And now you have to evaluate this expression, which you can see, you can work this out, is definitely going to be real. Okay, so here is the key idea. That to ensure that the norm of a complex number is real, you first have to take the complex conjugate of that complex number, then multiply it by the original complex number, get a result, take the square root of that, and that will be real. Okay. So what about the inner product? So suppose you have two vectors, u and v, and they are complex, not in a complex n-dimensional space, not in a real n-dimensional space, but in a complex n-dimensional space. Where capital C stands for complex. So we're now equipped to evaluate creatures like this. This is by definition the inner product of V with itself. You take the square root of that, and that equals the dot product of V with itself to the 1/2 power. And again, V is a n-dimensional vector, so it has n components. Clean that up a bit. But again, you see the same problem is in play. Problem is that this term could be imaginary, or any one of these terms. or all of these terms. So this is not the right prescription for how to evaluate the norm of a complex vector. We know what the right prescription is. We take the complex conjugate of each one of these coordinates, then multiply it by that coordinate, get an expression, and do the same for each one of the components of my n-dimensional vector, which is complex. And again, the rule is, as we've seen here, this guy is real, so the sum of these is real. So therefore, this whole thing will be real. That's good. That's what we want. Okay, so what about the dot product of u with v? That's the same as the inner product of u with v. Again, we're using Dirac notation here. Here's the ket, here's the bra. And as we discussed previously, Dirac notation, I think it's useful to introduce it here so that it's not a mystery when you see it in further courses, either on quantum computing or courses on quantum mechanics at some level. That's really all I'll say about Dirac notation. For the moment, we're just using it as a notational convenience. So what is this thing? So the inner product of u with v, where both these vectors are complex, is the dot product of u with v, and we know what that is. We know how to evaluate that. To ensure that this thing is real, we take the complex conjugate of u sub 1, multiply it by v sub 1, and do that for each one of the components of these two vectors, u and v. And we go all the way up to n, where n is the dimension of the vector. And our result is going to be real because each one of these terms is real using this idea. And then the final result is going to be real. Okay, so it's probably useful to sit down and, again, I mean, this is all going to be formalism, but it's going to be useful formalism. When we sit down and use all of this for applications, we get the formalism out of the way first, and we can then go down the road of looking at applications. So let's discuss the properties of an inner product of complex vectors in a little bit more detail. And here, for this example, I'm going to assume that u, there's always a possibility you can confuse the vector u with the vector v, so be careful. So I'm going to assume that u, v, v1, and v2 are all complex vectors. And I'm going to assume that the scalars alpha and beta are complex scalars. Okay, so let's move forth. Suppose we consider the inner product of u with a linear combination of vectors v sub 1 and v sub 2. So that's exactly what we mean by a linear combination. There is an important property of this inner product that you can exploit. You can break it down, or you can simplify it to the inner product of u with v sub 1 multiplied by the scalar alpha plus beta times the inner product of u with v sub 2. And this property of the inner product is known as linearity, or the inner product is linear. And this is easy to prove. and I may give it to you as a problem to work on in a subsequent problem set, problem set 10. The next property of the inner product, and again, we are looking at a bigger task here than we did in the previous lecture. We're allowing our vectors and scalars to be complex, not just real. Well, it turns out the inner product of U with V has a nice simple relationship with the inner product of V with U. And that relationship is that this inner product on the right-hand side, you have to take its complex conjugate for this equality to be valid. So this property has a nice name. It's commutativity. And again, this is easy to prove. And please recognize we've encountered commutativity before when we were looking at real vectors and real scalars. But the difference here now is that if U and V are complex, it's not just good enough to take this inner product and reverse the order. You'll have to reverse the order and then also complex conjugate the result. Okay, and finally, the inner product of a complex vector with itself is greater than or equal to 0. It in fact equals 0. So again, this is a scalar because the complex product or the dot product of two vectors at the end of the day has to give you a real quantity, and that quantity is a scalar. This is true if and only if the complex vector is in fact the 0 vector. And this is easy to prove. And I will ask you to do that in a subsequent problem set. And this property exploits the fact that the inner product is positive definite, that it is always positive with one exception, if the vector itself is in fact the 0 vector. Remember, the 0, U is a complex vector, and that just simply means that the real part of U is 0, and the imaginary part of U is 0. Okay, so I'm looking at properties of an inner product of complex vectors. So I have a lot of machinery already set up. And I can discover some other interesting properties. So what I want to do is start with equation 1. I'll rewrite it again. It says that the inner product of U with the linear combination of V sub 1 and V sub 2, where V sub 1, V sub 2, and U are complex vectors, alpha and beta are complex scalars, but this is alpha times the inner product of U with V sub 1 plus the complex scalar beta times the inner product of U with V sub 2. So let's start with equation 1, which I've rewritten as equation 4, and take the complex conjugate of both sides. And that's something I'm certainly allowed to do. So if I take the complex conjugate of equation 4, I get this on the left-hand side. And if I take the complex conjugate of the right-hand side, I get two terms. First term looks like that. And the second term looks like beta complex conjugate times the complex conjugate of this inner product. Remember, V sub 1, V sub 2, U are complex vectors, alpha and beta are complex numbers. Now, if I use equation 2, which says that the inner product is commutative. And since U and V are complex vectors, I need this complex conjugate on the right-hand side. Then equation 6 becomes the following. The linear combination now goes to the left-hand side of the vertical bar, becomes a bra. And U becomes a ket. And that has to equal on the right-hand side, alpha complex conjugate, V sub 1, the inner product of V sub 1 with U, plus the inner product of V sub 2 with U. Okay. And let's highlight this, because we want to use this. And actually, let's highlight this. This is really equation 1. I just rewrote it. Okay. So I want to discover some new properties of the inner product. So let's go through the following exercise. Let us set V sub 1 equal to V and V sub 2 equal to the 0 vector in equation 1. So equation 1 now becomes the inner product of U with alpha times V. And what happens is that alpha gets pulled out of the bracket. Remember, this whole thing is a bracket in Dirac notation, and alpha just gets pulled out in front, provided alpha was to the right of this vertical bar. And so that's an interesting property. It's interesting because if you contrast that to the situation where you set V sub 1 equal to V and V sub 2 equal to 0, the 0 vector, but now you do this in equation 6, what you discover is that the inner product of alpha times V with U is alpha complex conjugate times the inner product of V with U. And so the message here is that alpha is a complex scalar, and it occurs to the left of the vertical bar in the bracket. It can be removed from the bracket, but then the result is you have to complex conjugate alpha when you pull it out. Okay. So all this is nice, but you really don't know what's going on, or you really don't get a grasp of what's going on until you apply these ideas to problems. And you'll have ample opportunity to do that in problem set 9. But let's go to an example today in lecture. So consider two complex vectors that I'm going to write in column representation. I, as well as probably most people in this part of the galaxy, we will always write our vectors in column representation. That's the convention we're going to use. And so here are two complex vectors, the U and V. They are also 3x1 matrices. And you can see that some of the matrix elements are complex. The 1, 1, and the 3, 1 matrix elements here are complex. And here, all the matrix elements, 1, 1, 1, 2, and 1, 1, 2, 1, and 3, 1 are complex. And here, 1, 1, 2, 1, and 3, 1, only the 1, 1, and the 3, 1 matrix elements are complex. So these guys are 3x1 matrices. Vectors are matrices. So what is the inner product of U with V? Well, it is the U dotted into V. And as we've seen, what you have to do is complex conjugate all the terms in U to ensure that your complex vectors all have real norms, and then transpose that result and use matrix multiplication to multiply it by V. This is identical to taking all the components, U1, U sub 1, U sub 2, U sub 3, and taking their complex conjugates and multiplying them by V sub 1, V sub 2, and V sub 3, respectively. So let's do that. Let's spell it out. Here is U. Here is the complex conjugate of U. And here is the transpose of the complex conjugate of U. Here U is a 3x1 matrix. The complex conjugate of U is a 3x1 matrix. And here the transpose of the complex conjugate of U is a 1x3 matrix. So the task is to take this guy and multiply it by V, which has 3 matrix elements. And note, this is compatible for matrix multiplication. First one is a 1x3 matrix. Second one is a 3x1 matrix. So you should get a result, which is just a 1x1 matrix, which is just going to be a scalar. And again, it has to be real. Sorry, it doesn't have to be real. I'm just taking the inner product. I'm not talking about the norm. So it can be whatever it is. Let's find out what it is. Okay, so this is going to be 1 minus I times 3 minus 4I plus 3 times 1 plus I. I'm just using the normal rules of matrix multiplication, plus 4 plus I times 2I. Okay, and that's going to give me 4I. So it turns out that the inner product of U with V in this example is in fact complex. And that's okay, you know. As we'll see in a minute, we want to have the norm of a complex vector be real, but the inner product could be whatever it is. In this case, it's complex, or it's pure imaginary. Its real part is 0. Okay, so similarly, you could calculate the inner product of V with U, and you would find that you are left with the task of doing this complex multiplication, some steps in complex multiplication. And you would find that this is minus 4I. And this is interesting because it's equal to the complex conjugate of the previous result, as it should be. If you have the inner product of 2 vectors and they're complex, commutativity says you can write this as the inner product of the 2 vectors where the positions are swapped. What was a bra becomes a ket, what was a ket becomes a bra, but you have to include this complex conjugate on the right-hand side. Now, again, if everything holds through, you could calculate the norm or length of magnitude of U in this problem. And we know how to do that. Now we're getting comfortable with dealing with complex vectors. Sorry, that's not a 3. That is a complex conjugate. And I want to take the square root of that. And this turns out to be the square root of 28. And you should also show that the norm of V is in fact the square root of 31. Okay. All right, so now let's get to the second part of today's lecture. And again, you will have ample practice in dealing with these ideas in problem set 9. The only way that you can make sure that you understand the ideas and concepts we've talked about in lecture is applying them. Just sitting down and writing down the concepts or watching me write down the concepts is not the whole story. Okay, so matrices, so it's as advertised in the beginning of today's lecture, matrices do not just, let's get the English right. Excuse me. So matrices do more than store information, or in this case, information is in the form of numbers. Matrices do more than this. But let's pose this problem in terms of a question and try to answer it. What happens when you act on a vector V with a matrix A? In other words, suppose you look at this problem of matrix vector multiplication, and then you ask yourself, what do you get as a result? So this has an answer. The answer is it depends upon the detailed nature of A. Where here I'm looking at A as if it were to be an or if as if it acts as an operator. It does something to B. So let's go through some specific examples to see how this works out. So suppose you have a vector in R2. Let's go back to real numbers and real vectors now, make our life a little more simpler. And suppose I have a very specific matrix, a 2x2 matrix. It looks like this. So I can take this matrix A. So this is a matrix A. It almost looks like the zero matrix. It's just that the 1, 1 matrix element is 1. Or it almost looks like the identity matrix, a 2x2 form of the identity matrix, but the 2, 2 matrix element is 0. So I can tell you and anybody else exactly what this matrix does when it acts on V. All I have to do is use the rules of matrix multiplication. I have a 2x2 matrix and it's multiplying by a 2x1 matrix, so I should get an answer. My answer will be a 2x1 matrix. I can do that matrix multiplication, and I get a matrix that looks like this. The 1, 1 component is B sub x, the 2, 1 component is 0. But if I'm going to get some better insight as to what's going on here, I need to draw a picture. So here's my x-axis, here's my y-axis, and here's my vector v. So what's happening here is that when my specific matrix in this problem, A, acts on V, it does something to it. What it does is it projects V onto the x-axis. Excuse me. So A projects V onto the positive I hat axis. You can see that. Because if you look at the result, I get a new vector where V sub x is not changed, but V sub y now becomes 0. That's what I get when I took A and acted on V sub x. For the case where A was this very special matrix. This matrix A has a name. It's named after what it does when it acts on a vector V. This matrix we'll call a projection matrix. And what it does is it projects V onto the x-axis, but I have to be very careful because there are two directions. There's a positive direction and a negative direction. So it projects it on the positive x-axis. Okay, so we can look at other examples of matrices actually doing things. Again, I'm gonna stick with 2 dimensions. So I have an arbitrary vector in R2. And now I'm going to look at this particular type of matrix. It almost looks like the identity matrix, but now the 1-1 matrix element becomes 0. So the question is, what happens when this matrix A acts on V? And this is not an esoteric exercise anymore. I know how to answer this problem exactly. Just do the matrix multiplication. And I get a new matrix, which is a 2-by-1 matrix, where the 1-1 matrix element is 0, but the 2-1 matrix element is V sub x. And so if you really want to see what's going on here, I would suggest drawing a geometric diagram. In this example, example 2, when A acts on V, what it does is it projects V onto the positive y-axis. Or positive j hat axis. So in this case, example 2, my matrix A projects V on the positive j axis. I could probably call that positive. Well, that's fine. That's fine. I don't. That's the same as the positive y-axis. Okay, so semantics aside, this is also an example of a projection matrix. So you can see there are many kinds of projection matrices. And it does what it does is given by the name of the matrix. It projects the vector V on the positive J hat axis. Okay. So there are other types of, or other examples where matrices actually do things. And again, I'll start with my theme of either starting with a identity matrix or a zero matrix. And let's pick a simple example, an R2 two-dimensional set of real vectors. But now I'll turn the 2-2 matrix element of the identity matrix into -1. And I'm going to act on not one particular vector like I've done in, this is the same approach. I'm not just going to pick one particular vector in R2. I'm going to pick any vector in R2 and ask, what does this matrix do when it acts on it? I know the answer. I just have to write this down as a matrix equation. This is an example of matrix vector multiplication. We've seen these ideas before, so everything in this course is cumulative. We use concepts that we've discussed before for current and future applications, multiplication. So you can do this matrix multiplication in a snap, and you get a sort of strange result. The 2-1 matrix element has a minus sign multiplying it. But if you really want to understand what A is done, then I would suggest you draw a figure. Namely, in 2 dimensions, what this matrix does is it does nothing to the Vx component. It's still the same. But it turns the Vy component, so the Vx component is not altered. V sub x component is not altered, but the V sub y component is multiplied by a -1. So if I have to name this thing, what this matrix is doing is reflecting V through the positive x or I hat axis to give you a new vector. That new vector is just V sub x minus V sub y. Here's the original vector, V sub x, V sub y. So this is an example of a reflection matrix. And what it does is that it reflects V through the J hat axis. In this case, through the positive I hat axis, sorry. Okay. So there are 2 ways to do this. There's a algebraic way, which you just do the matrix multiplication. If you want to know what a matrix does to a vector, you can just do the matrix multiplication, get started with an answer, start out with an initial vector, and then you'll get a final vector. And then if you really want to understand what's going on, it's sometimes useful to draw a picture. And here you see that this is an example again, of a reflection matrix. So I will look at one more case. Imagine a identity matrix of order 2 where the 1, 1 matrix element, it becomes -1. What's going on here? Again, that's easy to figure out. Matrix multiplication comes to your rescue. And when A multiplies V, or when A acts on the vector V, you get minus V sub X and V sub Y there. And if you think about this and contrast it with the previous example, what's going on? Sorry. What's going on here is that V gets reflected through the positive J hat axis. So this, in example 4, is a case study of a reflection matrix where V is reflected through positive J hat axis. Okay, so we have looked at least two examples where matrices can actually do things. We've looked at the example of a projection matrix, and we've looked at the example of a reflection matrix. And they do exactly what they say they're going to do, given their names. So we'll take a break now, but the next thing we want to do is look at matrices that rotate vectors, the so-called rotation matrix. So we'll take a break and resume again in about 5 minutes. Okay, so let's resume where we left off. So this fifth example of matrices doing things involves the introduction of a rotation matrix. And as you might imagine, a rotation matrix is going to do exactly what you would think it would do. So let's look at this in 2 dimensions, R2. Here are my unit vectors, I hat and J hat. So what my rotation matrix is going to do is, suppose I have a vector R sub 1 that looks like that. And suppose I want to rotate this vector so that I get a new vector, R sub 2. So R sub 1 is my initial vector, and R sub 2 is my final vector. And I want to rotate R sub 1 by some angle theta in a counterclockwise direction, such that the magnitude, or norm of R sub 1 is the same as R sub 2. So let's tackle this problem a little bit more carefully. R sub 1 is going to have two components, x sub 1 and y sub 1. And I can write it as a vector in column representation. And R sub 2 is going to have two components, x sub 2 and y sub 2. And I want to write her as a vector in column representation. And so let us do exactly, let me write down exactly what we're doing. What we want to do in this problem is rotate R1 about the origin by some angle theta in a counterclockwise direction. And let us find the matrix that performs this operation. So we've described the operation that we want to do, and hopefully that can give us some insight in discovering what is the matrix that actually does that. So let's go back and look at this figure. I'm going to define a vector alpha, or angle alpha, that goes from the positive x-axis to R sub 1. So if I look at this diagram, here is R sub 1. It has components x sub 1, y sub 1. Here's R sub 2. It has components x sub 2, y sub 2. Excuse me. I can write x sub 2 as R cosine of alpha plus theta, and y sub 2 is R sine alpha plus theta. So all this comes from my diagram, from my picture. Pictures tell you things. X sub 1 is R cosine of alpha, and y sub 1 is R sine of alpha. So what are we trying to do here? The goal is that we are given x sub 1 and y sub 1, and we want to find x sub 2, y sub 2. And in particular, we want to find the matrix that acts on R sub 1 and turns it into R sub 2. So we're going to need some tools. Euler's formula is going to be very useful. We've introduced it before. E to the I theta is the cosine of theta plus I sine theta. Therefore, e to the I alpha plus theta is going to equal the cosine of theta, cosine of alpha, minus the sine of theta times the sine of alpha, plus I times the cosine of alpha times the sine of theta, plus I times the sine of alpha times the cosine of theta. So I'm going to ask you in problem set 9 to show that's true, prove that, and eventually show that x sub 2 and x sub 1 can be simplified and written in terms of r, alpha, and theta. The result is that x sub 2 will be r times cosine of alpha, cosine of theta, minus r sine alpha sine theta, and x sub 2 will be r sine, let's write this a little different form. So it has some similarity with the previous guy. R cosine of alpha sine theta plus r sine alpha cosine theta. And again, I'm going to ask you to use a result that you got from trigonometry that tells you what x sub 1 and y sub 1 are in terms of alpha by looking at the diagram. And we have an interesting final result. Again, we want to figure out what x sub 2 and y sub 2 are in terms of x sub 1 and y sub 1. And here's what they are. X sub 2 is x sub 1 times the cosine of theta minus y sub 1 sine of theta, and x sub 2 is x sub 1 sine of theta plus y sub 1 cosine of theta. And so this is a result that you're going to prove in the problem set. So why is this useful? This is useful because now we can write down a matrix that in fact takes the vector r sub 1, acts on it, and gives you the vector r sub 2. And what is that matrix? It's a 2 by 2 matrix. And its components are cosine of theta minus sine of theta, sine of theta, cosine theta. Got a little sloppy here. So let's recast these vectors a bit. Okay, so over here on the right-hand side, I have r sub 1. And here on the left-hand side, I have r sub 2. The 1-1 matrix element of this matrix is cosine of theta. The 1-2 matrix element is minus sine theta. The 2-1 matrix element is sine of theta. And the 2-2 matrix element is cosine of theta. So this matrix is what we'll call the rotation matrix. And it clearly depends upon theta. And it does exactly what we want it to do. So in fact, what we have discovered in this example is that if you give me a vector r and you act on it with the rotation matrix, you will get a new vector r sub 2. Note that the rotation matrix does not change the length of the vector as it rotates it. And in fact, this rotation matrix, at least for this example in 2 dimensions, has a dependence upon theta that looks like this. So let's write again in words what this is. R is a rotation matrix where the R stands for rotation. And so this rotation matrix rotates, does what it's, to figure out what it does, you just look at the name of it. It rotates a vector in a counterclockwise direction. So the way we built or constructed this thing, we looked at a specific direction where that rotation is occurring by an angle theta about the origin. Okay. So we've constructed this rotation matrix. Let's look at some properties of it. Created this creature. It does what we want it to do. But now let's stop for a minute and look into the inner heart of this matrix and see what it's doing. So again, the rotation matrix in 2 dimensions is the following. So we want to play with this matrix. It's a very special matrix. And we want to explore what it's telling us. So one of the things we could do is take its transpose. That's easy. We just interchange the 1,2 matrix element with the 2,1 matrix element. And now this is something that you will get that's fascinating. If you multiply the rotation matrix by its transpose in any order you want, you can show that the result will be the identity matrix. And again, I leave this to you as an exercise in problem set 9, which will be available at the regular place on the web tomorrow. But look at this. Here's the product of 2 matrices, and it doesn't matter which order I multiply these guys, I get the identity matrix. So I should think about this for a minute. This is telling us something very special about the rotation matrix. It's telling us that when I look at the rotation matrix and take its transpose, I get exactly what I would expect if I took the inverse of the rotation matrix. So the rotation matrix has a very special property. If you take the transpose of the rotation matrix, you will get exactly what you would get if you wrote down the inverse of the rotation matrix. Any matrix that has this property is known as an orthogonal matrix. So if you have a matrix A and its transpose equals its inverse, then that matrix is orthogonal. The rotation matrix is an example of an orthogonal matrix. So as you'll see in problem set 9, there are many, 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 many types of matrices, many kinds of matrices you can write down that are orthogonal matrices. Rotation matrix is a very special example of an orthogonal matrix. So what's the big deal? Why is an orthogonal matrix important? Does it have some other underlying property that makes it very, very useful in linear algebra? And it does. We'll write this down and prove it in a minute. Orthogonal matrices have the very important property that when they rotate a vector about the origin, they preserve the length or norm of that vector. So let's highlight that. So orthogonal matrices have the important property that when they rotate a vector about the origin, they preserve the length or norm of that vector. Okay, so let's look at a proof of this. So what are we trying to do? I give you a vector u, and I act on it with a orthogonal matrix. And one example of an orthogonal matrix is a rotation matrix. So what the orthogonal matrix is going to do is take some initial vector u and rotate it to some new vector v, such that the length or norm of v is the same as the length or norm of u. So that's really inequality. So I need to prove that the norm of this final vector v is the same as the norm of this initial vector u. So how am I going to do that? Well, let me just use all the ideas that I've talked about so far. The norm of v is just going to be the inner product of v, and I'll take the square root of that. If I just look at the square root of it as an operation, this is just going to be proportional to the inner product of v with itself. I know exactly what this is. This equation tells me that the bra v is just A acting on u, and the ket v to the right of the vertical bar is just the matrix A acting on u. That is, by definition, the dot product of A times u with itself. This dot product, I'm using arrows here, so I'm using a equal sign, so not necessarily arrows. That is the same as the transpose of this matrix times the original matrix. I know how to take the transpose of the product of matrices. That's just the transpose of u times the transpose of A. And now let's make an assumption. Suppose the transpose of A times the transpose of A equals the identity matrix. So that's a big F. So we're making an assumption here in this proof. So let's assume that that's true. So if that's true, and there's a good reason for assuming it's true, you get something interesting out of this, right? You get, there's a subtle step that I've skipped, so I'll put it back in, no problem. I'll get that the transpose of U times the identity matrix equals U, and that's simply this, and that's simply this, excuse me, and that's simply this, and that's proportional to the length of U. So what I have shown is that if A is an orthogonal matrix, that is to say, its transpose is the same as its inverse, then the norm of V is the same as the norm of U. A rotates U by some angle, but it doesn't change the magnitude of U. The magnitude of U is the same as the magnitude of V. Okay. Now, there's something else that you can glean from this discussion. And I will sketch this out here, but I will leave the proof to you in problem set 9 or 10. Suppose you have two vectors, X and Y, and suppose you have an orthogonal matrix A, which acts on both the vector X and the vector Y, keeping their magnitudes or lengths unchanged. Well, you can prove, and I'll give you some hints on how to do this. This will be on the next problem set 10. You can prove that theta, this angle between X and Y, is also preserved. And you might say, well, you can look at this figure and you sort of can see that that's probably right. But it's probably more useful to, in fact, prove this, where the proof is similar, but not identical, to the previous case that we looked at. Okay, more questions. Why do we call our matrix A an orthogonal matrix? I mean, we know what orthogonality means with respect to vectors, but how do we take this concept and apply it to matrices? What does it mean if a matrix is orthogonal? So let us return to our friend. One example of an orthogonal matrix, the rotation matrix, and let's write it down. In 2 dimensions, it has 4 matrix elements. One matrix element is cosine theta, the 1,2 matrix element is minus sine of theta. The 2,1 matrix element is the sine of theta. And the 2,2 matrix element is the cosine of theta. Now let's do some microsurgery. This is column 1. This is column 2. This is row 1. This is row 2. So I could write column 1 as a column vector. I've done this before in other examples. I could write column 2 as a 2 by 1 column vector. And one of the things that's easy to see is that if you calculate the norm of these two vectors, you get the same result. Namely, you get 1. Similarly, if you took the rows of the rotation matrix in 2 dimensions and wrote it as, or express those rows as vectors, again in column representation. So here's R sub 1, and here's R sub 2. It is easy to see, again, I leave it to you as an exercise, that the norm of row 1, vector row 1, equals the norm of R sub 2, which equals 1. The next observation you can make is that if you ask what happens when you take the dot product of column 1 with column 2, that's just the transpose of the matrix C1 times C2. And that is exactly a cosine of theta, sine of theta for the first matrix. The second matrix is a 2 by 1 matrix that has these matrix elements. So this is a 1 by 2 matrix element, 1 by 2 matrix. This is a 2 by 1 matrix. And you can show that in fact, that is 0. The scalar 0. And furthermore, it doesn't matter what the order of the matrices are. You could take the dot product of C1 with C2 or the dot product of C2 with C1. The dot product is commutative. You'll still get the same answer. And you can take this trick and apply it to the row vectors using exactly everything we know, what we've learned so far. This is going to be the cosine of theta minus sine theta times sine of theta cosine theta. These matrices are compatible, and this again is 0. This is a 1 by 2 matrix. This is a 2 by 1 matrix. So now we see why we call this matrix an orthogonal matrix. An orthogonal matrix is made of columns or rows, and rows. So either column or row vectors, singular, that are orthogonal to each other, and furthermore, each vector, be it either a row vector or a column vector, has a norm of unity. So now we see exactly where we get the idea of calling this orthogonal matrix an orthogonal matrix. We bury inside of it, for this one example, that is true for any orthogonal matrix. We won't prove that here, but the state is true. The row vectors or the column vectors are orthogonal to each other, and each vector has a norm of unity. I'll just say as an aside, you might ask, well, why should you call this an orthogonal matrix? Why not call it orthonormal matrix? And that sort of logically makes sense, but that's not what people do. People have tended to call this thing a orthogonal matrix, simply because any two row vectors or any two column vectors are orthogonal to each other. So let's summarize where we are. We have discovered in case 5, a special type of matrix, a rotational matrix, or an orthogonal matrix. Orthogonal matrices rotate real vectors by keeping their magnitude unchanged. So the final thing we have to take care of, the cleanup, is this is fine if our vectors are real. What happens if our vectors are complex? And there are a lot of cases in linear algebra where the vectors in a problem turn out to be complex. You're not restricted to living on the real line, on the real axis. You can venture off and look at other parts of the complex plane. So, suppose U and V are complex vectors. Where this epsilon symbol means belongs to the set. And complex numbers are different than real numbers. And so we'll use a capital R for real and a capital C for complex. So let's say U and V belong to, in our review, U and V are vectors in an n-dimensional set of complex numbers. Or really coordinates or components. So what does that mean? Well, I can take the dot product of U with V, and I know how to do that now. I have to remember that I want the norm of any complex vector to be real. So to ensure that that's what's happening in play, I have to use my trick of taking the complex conjugate of the first component. And now I go all the way up to n. Similarly, I can look at another way, an alternate way of writing this down. U dot V, dot product on U with V, is the inner product of U with V, and it is the transpose of the complex conjugate of U times V. And so it is, we'll write this in terms of matrices. This is what I have. Let's check the matrix multiplication. This creature on the left is 1 by n. This is n by 1. So that's going to give me a 1 by 1 matrix, or it's going to give me a scalar. And again, the norm of U is just going to be the complex conjugate of U sub 1 times U sub 1 plus the complex conjugate of U sub 2 times U sub 2. Add all that up to the complex conjugate of U sub n times U sub n, and take the square root of this. And that's always going to be a real number. Okay. So what happens if I take an orthogonal matrix? Well, let's just say, I take a matrix and I multiply it by U to get a new matrix V, where the norm of V is the same as the norm of U. And unlike the previous case, U and V are now complex. So this is a whole new ball game. Before the previous case, if I wanted to do this, turns out that A had to be orthogonal. It had to be an orthogonal matrix. But that was only true if U and V were real vectors. Now let's look at the case where U and V are complex vectors. What can I say about A? Well, the proof is going to be very similar. I just have to be careful. I want to calculate the norm of V. That's going to be proportional to the inner product of V with itself. Again, by just using this definition here, that is A acting on U times A acting on U. That is simply the dot product of A acting on U with A acting on U. And again, using the rules of matrix multiplication for vectors, where these guys are complex, that is the following. So I don't know anything about A other than the fact that U and V are complex. A might be real, it might be complex, it might be partially real. Well, it may have matrix elements that are complex, it may have matrix elements that are real. So the safest thing to do is assume I know nothing about A other than it's a matrix, and it satisfies this matrix vector equation, and it satisfies matrix multiplication. So far, all I've done is pay attention to the fact that everybody could be complex here. So again, we've done a similar proof of like this before. I know how to evaluate the transpose of the product of those matrices. It's just this. And now I can see where I want to go. I want to basically make sure that the norm of V is the same as the norm of U. The only way I'm going to do that is if the transpose of the complex conjugate of A times A equals the identity matrix. Because if that's true, then I simply have that, which is the same thing as this, which is the same thing as this, which is the same thing as this inner product, which is proportional to the norm of U. And I have a proof that says that the norm of V is the same as the norm of U once I act on U with A, provided that this condition is true. So let's write this out. For the norm of V to be, norm of V is proportional to the inner product of V, which is proportional to the inner product of U, which is going to be equal to this. So for these guys to be equal, we must have the following equation in play. The transpose of the complex conjugate of A has to equal the inverse of A. Now, I don't know about you, but this is a lot of notation to carry around. So I'm going to make my life a little simpler. I'm going to call the transpose of the complex conjugate of A, or recognize that the transpose of the complex conjugate of A is the same thing as taking the transpose of the matrix first and then taking its complex conjugate. I'm going to come up with simple notation. I'm going to use this superscript of a dagger. So again, please, T is transpose. That's not the same thing as dagger. And I'm going to call this dagger an operation. I'm going to give it a name. And it's called the Hermesian Conjugate. So the Hermesian Conjugate means you take the complex conjugate of something and then you of a matrix, and then you take its transpose, or you could take its transpose first and then you take its complex conjugate. So we have discovered that if you have a matrix A that satisfies this condition, that its inverse equals its Hermesian conjugate. So on the right-hand side, I have the Hermesian conjugate of A. On the left-hand side, I have my friend, the inverse of A. If those two properties, if this equation is satisfied, then A is a very special matrix. It is called a unitary matrix. Okay, so let's summarize everything we've talked about in the past 40 minutes or so. So let's make a nice little table. U, V, and what happens when a matrix A acts on U to get V. Okay, so there are lots of examples you can imagine getting. Construct this table. Suppose U and V are both real vectors. And it doesn't matter whether U is in 2 dimensions or 3 dimensions. It could be an n-dimensional vector. So if in fact A is a orthogonal matrix, then what that means is that the norm of V is preserved. When you act on U with A to get a new vector V, you don't change its magnitude, you just rotate it. Formally, this says that this means that the transpose of A is a matrix that equals its inverse. Let's contrast that with the case where U and V are complex vectors. If you want, in this case, the norm of V to be preserved, in other words, the norm of V is the same as the norm as U, norm of U, the vector U, then A has to be a unitary matrix. And what that means is the inverse of A has to be equal to its Hermesian conjugate, where this is just transpose complex conjugate or complex conjugate and then transpose. Doesn't matter which one you do. So that these ideas will sink in. You'll have lots of examples of practicing this in problem set 9. But let me end with the following question. Why do all of this? What's so important about orthogonal and unitary matrices? Why are they useful in linear algebra? So that's the question. Here's the answer. The inverse of a matrix is something that you will need lots and lots of times from many, many applications in linear algebra. And we've found ways to calculate it, at least one way. But it's hard to calculate this for large matrices. I mean, Google has inside of it code that deals with square matrices that are of the order of n, where n is a billion, for example. And taking the inverse of that is something that you want to avoid. No computer scientist is going to sit down and try to write code to do that. So what we have discovered is that if you can come up with special matrices like orthogonal matrices, then taking the inverse of A is simple. All you have to do is take the transpose of A, which is easy to do. Transpose of a matrix is a very easy thing to do. And again, this is true if the vectors are real. Same story if the vectors are complex. Well, similar story, not the same. Calculating the inverse of a complex matrix is a task that you just don't want to do in a real application. We've done it for simple matrices of order 2 and 3, and maybe even 4, but larger matrices, you don't want to do that. So what we have shown is that if you can find the Hermesian conjugate of A, then that's equivalent to the inverse of A. Or said more broadly, if A is a unitary matrix, where its inverse is in fact equal to its Hermesian conjugate, then it's very easy to calculate the inverse of A. All you have to do is take its transpose, which is easy to do, and then take the complex conjugate of all the matrix elements, or you could take the complex conjugate of the matrix elements first, and then take the transpose. So again, problem set 9, which will be available on the website tomorrow, gives you practice with working with these matrices. And again, to conclude, we've looked at special types of matrices, where matrices actually are actors. They do things. And we've looked at a number of them today. We've looked at projection matrices. We've looked at reflection matrices. We've looked at rotation matrices. We've looked at orthogonal matrices, with the rotation matrix being a special case of orthogonal matrix. And we've looked at unitary matrices. Where orthogonal and unitary matrices have one thing they do in common: they preserve the norm of the vector. When you start out with U, and you act on it with a matrix A to get a new vector V. Okay. So this concludes lecture 9. And again, the solution key for problem set 8 is available, or will be available tonight. And the problem set 9 will be posted tomorrow, sometime late tomorrow afternoon. Thanks very much for your attention.